Swayam Prabha. Digital India. Educated India.
In the summer months, right? Yellow is 2023, red is 24 this year. We have, and the range is given in the white bar. On an average, we've had hotter summers this year as compared to last year. This year has turned out to be one of the hottest years ever. Right? If you think of the effects what we have, this is year after year. This is from, one sec, sorry about that. This is from NASA. So these are all the years plotted up one after the other as an animation. That's starting from 1930s onwards. That in red is 2023. The change is accelerating. 2024 looks to follow that, but most probably it will surpass that. And the troubling part really is that they are significantly above everything that we have measured. And that's the part which is really alarming, because we don't know why the system is accelerating. That's the part where climate scientists, I am not a climate scientist. I look at the data and I look at that and say, okay, this is interesting. This is how it will guide what my research will be. But there are people who study this for a living. They collect data, they analyze these data, they put these things together. And what has been puzzling is, in the last 2 years, the system seems to be getting hotter faster against everything that we had imagined it will do. Okay. So this is what it is today. And the temperature, this thing starts from, I think it was in the previous animation, the GIF was from 1932 onwards. That's when they started making these. Not only in the summer months, but every month has come up a little higher. Okay, so if we are studying this system, here's what we look at. It's, at the end of the day, it is basically counting up what radiation we get. The major source of energy for us is the sun. So the heat that we have, heat that we get is from the sun. We get the sun rays coming in. We have some amount of radiation that is absorbed. Some of it is reflected. So we do basic mass balance, pretty much a mass balance of incoming versus outgoing radiation. So if you look at that system together, that's really what we're looking at. We have incoming sun rays. We have cloud cover, so some of it gets reflected back, doesn't make it to the earth. Whatever does come back down to the earth is measured in the numbers. These are numbers, watts per meter square. And in parentheses here are the uncertainties in the numbers. These are huge numbers, right? So we're looking at these numbers. It gets absorbed in the surface of the earth, and the earth then radiates heat back out. And that's what we are trying to balance. Ideally, for temperatures to be maintained what we have, the energy balance should be met. There should be no excess energy. Whatever we get in is what we radiate out. Yes?
How do we exactly know that 340 is coming in?
Yes, Yes, so that's it's an excellent point. We have satellite measurements. We have measurements that we do at various levels in the Earth to measure these things, and these are carefully measured numbers with large uncertainties. So that is there as well, and the uncertainties are in the measurements, in cloud cover. Clouds are by far the most difficult ones because they are transient. You don't know how much you have. So cloud cover is what will give you what's reflected out in addition to every other reflection. So that's something that we cannot control. We can control, not control, we can measure what we're getting from the sun through radiation measurements. When we do all of that, we see that there is a slight imbalance, zero 0.6. Now, you might say, look at the uncertainties in the numbers, that is pretty much lost in the equation, but yet there is a slight imbalance. That little imbalance, that small imbalance, is what's giving us the increase in temperature. So, ultimately, if we are trying to game the system, then we want to be tweaking this here. We want to be tweaking how much of radiation are we getting in, how much is absorbed. So land cover, for example, if we plant things with very high absorptive power capacity, we will have more absorption of heat, not so much, a lot of it will be trapped. If we have some things that has very high albedo, we will radiate everything back out, so we will not trap much heat here. If we increase cloud cover, for example, we seed the clouds, so we have more of a cloud cover, we will have less coming down because most of it is being reflected. Those are some of the geoengineering proposals out there trying to do that. China has tried one of these systems or is planning to try. I forget, I didn't keep track of them, but there is a plan to seed and create clouds so that you get condensation points. You put nanoparticles out in the atmosphere, they form condensation points, and so you get a cloud cover that increases the amount of reflected sun rays. So it doesn't even make it to the Earth, right? So those are some of the things that we do. But ultimately, we're looking at the system here. Ultimately, we're trying to map this one here with what heat is radiated out and how much of an imbalance we have. Remember, it cannot be very much an imbalance because otherwise the temperatures would rise too much or will decrease too much. If we didn't have any clouds, we would absorb all of the heat and this would be a much higher temperature on Earth, right? So when we look at these systems, we try and balance the budget. We try and look at the amount of solar intensity. This is well known, this is well measured. These are fairly constant numbers and they're not going to change very much soon. Sun is not going to change in a short period of time. This part will change. And that depends not only on the cloud cover, it depends on volcanic eruptions, it depends on what we are doing to the greenhouse gas emissions. It will depend on cloud particles or nucleation of condensation that would give you clouds. So you have certain amount of clouds, and now we look at the effects and we call them forcings. You have positive and negative forcings. Forcings are something that that impinge on the system, that work on top of the system. A positive forcing is a reinforcement. A negative forcing is an impediment. Right? So clouds give us negative forcings. We are reducing temperatures. Right? We have ozone depletion that has some effects but not very large. So that is also a small, very tiny negative forcing. We have the greenhouse gases, and those have the biggest effect that we can calculate. Okay? And so, and then we have land use change that changes the albedo of the system. And so that when we go from forests to farms, when we have cement and concrete in many places that used to be land cover with forests, that changes the albedo, changes it but substantial amounts. And so this is a known effect. The overall effect is not that large. It still counts up. So when we are looking at the changes, we want to be able to balance the system. This pretty much what energy we're getting in is the energy that we're looking at going out. And so we look at all of the natural and forced variability of the system. What is a natural system? What's forced? All of the greenhouse gas effects are forced. All of volcanic activities, whatever happens due to forces within the earth, is a natural system. It is there, it will be there, it has been there. Something we cannot control. We can try and tweak it, which we try and do. A lot of times we will try and do that. But for the most part, we can measure and we can identify, oh yeah, this was a major eruption in Iceland, the volcano which no one can pronounce, about 7-8 years ago, or the major eruption in Krakatoa. All of those we can trace for their cooling effect, because you had suddenly a large amount of volcanic ash in the atmosphere that gave it a blanket effect. So we didn't get enough sun rays coming in, which gave us a cooling effect. And you can track that. So it's fascinating to be able to do that. You have Alquichon, you have Pinatubo. All of these are trackable events on the global average surface temperatures or the average surface temperature anomalies. Because if it has a cooling effect, these are negative forcings, and we see them on the gust, right? So the part where we try and make sense of is where we have a mixed signal, where we have signals that are coming from human-induced activities and the natural system, the natural variability imprinted on top of it. As you might know from working with multiple signals, multiple inputs, trying to piece out and ascribe contributions from various systems onto a measured anomaly becomes very hard. And so the argument sometimes in looking at climate data comes in because of the way we interpret, the way we assess the changes that we are measuring. The measurements are real, we have those. It's the reason for those changes where we have a difference in opinion many times. Not just a difference in opinion, but a large difference in the way we think about these data. So what are these forcings? And you will hear these. If you look at the climate data, if you study the Intergovernmental Panel on Climate Change, IPCC, or Conference of Parties, COP, COP29, which is happening now, where people are discussing that. Those are all United Nations bodies that have gotten together to say, there is a problem, we need to study that. The IPCC panel brings out assessment reports. This happens every few years, where a lot of scientists get together. All they're doing is analyzing what has already been published. They're not doing work themselves, they're looking at what published work, research that has been published on climate markers, right? In that, when you're reading those, you will look at forcings. What are changes that are happening to the climate system? And so when we look at positive forcings, those are the ones that will give us not just, it will give us a warming effect. And so, sun can always get warmer, but it's not going to happen. So this one we can rule out. We can emit more greenhouse gases that will give us a positive forcing. That means less energy will escape because we are trapping it in the greenhouse gases. So, and that is happening, and we can measure this. There could be orbital shifts, Milankovitch cycles. There are changes from glacial to interglacial ice ages and so on. These can be happening. These are natural forcings depending on which way you're going. If you're going from an interglacial to a glacial period, you have a negative forcing. If you're going from a glacial to an interglacial one, you're going to a positive forcing. And you have volcanic eruptions that release a lot of greenhouse gases, and so they will add to the atmospheric greenhouse gases. We can get negative forcings. The sun gets cooler, again not happening anytime. Volcanic eruptions put sulfur in the atmosphere, which we know they do, and so that those particles that are up there, they increase the albedo. And so we get much more incoming sun rays that are reflected back. They don't make it to the earth. And so we get lower solar energy that is absorbed into the system. That gives us a negative forcing, which means it leads to a cooling. Again, we get orbital shifts. We're going from an interglacial to a glacial state, and we can change the land use, more urbanization. So if we do that, then this reflection of sunlight changes, and so that can lead to, depending on which way we are going, either we are deforesting or we are afforesting, right? So whichever process we are following, we will change the albedo, and so that will give us yet another effect. Yes, the reflectivity. So when whatever you have incoming sun rays, and they get reflected back, so that is high albedo. If you absorb it, so white bodies have high albedo, they're reflecting everything out. Dark bodies are absorbing more, they have low albedo. Right? So that's
here we are taking care of CO2.
Yes.
What about other greenhouse gases like methane,
Yes.
SO2, and
excellent question. Keep that at the back of your mind and thank you for pointing it out. I'm talking about CO2 all the time, and we are sloppy with our terminology. When I say carbon dioxide, I mean carbon dioxide equivalent. So we take carbon dioxide as the baseline, and we say the warming potential for carbon dioxide is 1, and everything else compares to it. So for example, methane is 27 times more effective as a greenhouse gas than carbon dioxide. So you're very right. So we would multiply. Yes, but we're looking at, if you burn it, yes, you will convert it. But when we're looking at the atmosphere, when we're looking at the warming potential, we're looking at the potential of that methane in the atmosphere, right? So we're looking at how much warming does that, how much heat can that trap, and how much does it warm when you have methane in the atmosphere. So that's really what we're talking about when we're looking at SOx, NOx, or methane or carbon dioxide. We bring everything down to a carbon dioxide equivalent. And so when we say carbon dioxide equivalent, it's understood that all the other gases are in there, factorized by their warming potential. That's an excellent point, though. It says, so when we're looking at the sensitivity, we're really looking at all of the feedbacks after they've been taken care of everything. We look at what remains and what can be ascribed to carbon dioxide. One of the things, and we'll look at data, what we had compiled in 21. That was the last measurement was in 2010 for ocean warming. And I pulled up the data again about a week ago, and it was alarming at how much more that has changed. Whatever's happening in the oceans takes a long time to appear, and it takes a very long time to dissipate. Oceans are heat sinks. If we heat up the oceans, they are not going to cool very quickly. This takes tens of years, centuries to appear, and takes even longer to disappear. Okay? So when we're looking at the climate equilibrium and transient signals, we're looking at every one of these. So we're trying to ascribe each one of those effects, count everything up, prepare a careful status for every country. That's really what we are looking at. And I have a number of links for you to pursue if you wanted to study the status of every country on where they are, on their warming potential, on their land use, on their energy use, and on their greenhouse gases, both mitigation as well as generation. It will be really useful if you wanted to pursue that. Now, all of this is status today, but we want to know until 2100, till 2050 at least, what is the climate going to be like in 2050? And so that's where a lot of the theoretical models come in, and we have a lot of work that's been done today in machine learning. People are looking at data, compiling. We have a lot of data, and we know what to ascribe them to, so we can take care of all of the transient signals. Whatever remains is what we model as a long-term prognosis of how our temperature will be in 2050, in 2100, and so on. And so what's very interesting is these models used to be different up until about 1980, 1990. In the recent 10, 20 years, they have gotten much more sophisticated. They're putting in many more components of it. And regardless of which climate group you look at, those model prognoses are very, very similar. And so it gives us more confidence. Maybe the data, the prognosis, the predictions are not that great, but we have more confidence in those predictions. And that's really the part that is interesting, because all of those models are pointing towards a warming future. The recent data, what I showed you about 5 or 7 slides ago, with 2023 and 2024 showing an acceleration, are not covered by the models. And that's the part that is alarming most climate scientists, because that is something in the system that does not make sense today. Doesn't, I'm sure if we were to follow this, people have theories of why it's happening. I have not followed this. I just looked at the data and realized, oops, we have a problem. 2021, 2022 is not the same, and you blink and everything has changed, and 23 and 24 pose to be a problem. So for me, the curiosity now is, why did it change? And what are climate scientists saying about the change? Okay? And for you, I mean, if you are really interested to pursue that, I would look at that change in 23 and 24 and look to see, why is there an acceleration of the change, right? So it seems almost there is a baseline, and then things are changing. It looked to be more linear, but it seems as if the change is going more from linear to an exponential increase, which would be pretty dramatic. It's not what we want to see. So these are ensembles of data, and we see here That's the uncertainty here. So this is the mean, these are the observations, and this is the spread. And this spread is coming closer together as we progress on with our climate models. Okay, so what do the models tell us? So you can do simulations. So these are simulations, 1850 up to 2020, and I'm sure there are newer ones. Simulations of what the temperature would be if we had only natural activity. That means we have sun rays coming in, we have volcanic activity, all of that built in. So we have only natural forcings at play. And if we do that, then this is what the range looks like. It's sort of fluctuating on around 0, plus minus a little bit, but more or less around 0. If you simulate the changes and add in human activity with greenhouse gases coming in, that's what it looks like. So there is the last IPCC panel published a report that was, this is multiple countries, everyone wanting to get their points of view across. After much wrangling and fighting, they could agree on the word unequivocal. That means there is no doubt about it, that the climate is changing, and the change is due to human activity. And part of the arguments that allowed them to make the decision were models like this. Models like this, where you could model the climate system to say, this is what it would look like if there were only natural forcings at play. And they could also, it's not just enough to do one proof, you need to do a positive and a negative proof. So this was the way to say, here's the only way that we can match what we are observing with time, with the temperature anomalies. And if we remove that, then there's no way that we can match it. Just a natural system with volcanic activity, with El Nino, La Nina, all of these changes that are the weather patterns that happen year after year, if you put all of those into your climate models, you get something that fluctuates around 0. And so this is the IPCC. This is the Intergovernmental Panel on Climate Change. It's a United Nations body. You can download these reports. They are available to anyone who wants to read them. These are thousands of pages long, and they know that no one will spend time reading thousands of pages, so they give a summary. And the summary is a couple hundred pages long. And then with the summary, they also have an executive summary, which is half a page, 2 pages long. So most people read the executive, most people just read the title. Some people read the executive summary. So, and many read the assessment report summaries. Very few people, except for the ones who wrote them, read the thousands of pages. Yet there's a trove of data and assessments in there. They inform a lot of the decisions, a lot of the directions that every country is taking. Right? Okay, so now we look at the IPCC assessments and the models that they are creating, because remember, we're trying to work our way through to say, how do we get to these emissions control, right? We're looking at climate data. So we need to come to a conclusion on how are we going to control it. But before we can control it, we need to understand what are the interrelations, what's the cause and the effect. So when we look at these are models, these are different scenarios that give us the amount of emissions control that we need to put in place to have a certain temperature target. So these are different models. This is my GAST, and we're looking at predictions. This was here done somewhere around 2015, 2014. And the models here are predicting going forward how much of a change should we expect given the amount of emissions control that we will put in place. And we will look at this in more detail. If you don't do anything, if you only do your nationally declared contributions, if you do a more aggressive updated contributions, if you do capture, and if you try and do a much more aggressive capture and an energy transition. So these are the types of things that we need to do to be able to. Each one of these models has implications of what we have to do to be able to control the temperature so that we reach 5 degrees above GAST, right? Average temperature doesn't mean it is going to be 5 degrees everywhere. This is the average change. In some places it could be less, in some places it could be much more. And if you're interested, there are maps that are created on where temperature, let's say today we are at, we had the data from earlier, we are at 1.2 degrees above. The anomaly is 1.2 degrees above pre-industrial times. There are maps in the IPCC that are really interesting, global countries, continents, and the oceans that show where did we go above that 1.2 degrees centigrade, where were we below. And the alarming thing is usually those temperatures are changing a lot more on the permafrost. So I'm sure you've been reading about glaciers that are melting, that are not staying there. The ice sheets that are carving off from Antarctic, right? And there are these, what people are now seeing are below the permafrost, there is a water layer which is lubricating those sheets to flow faster into the ocean and break away. So we have much more breakage of that permafrost that is really causing alarming challenges. These are some of the models that allow us to predict cause and effect. Or say, if we are going to change, if we don't do anything, this is what will happen. If we change something, here's what will happen, and so on. So that we can design our strategy, the national strategy, based on what we are willing to do. And in a way, it's not just national strategy, right? It has to be a global strategy. Because it doesn't matter if you don't emit and I'm emitting happily. There is no such thing as this is the Indian atmosphere and this is the Australian atmosphere. It is one atmosphere. So we will have to come together as a world, as a globe, and solve this problem. Okay. I think we went over this, right? How do you construct the anomaly? And I think we might have data. What we can do is I can make sure we have emails from everyone, right? Okay. We will send these slides. We send PDFs to you because otherwise the slides are too big, and a template with one place data. And I hope that you can create your own anomaly and put that on top of what we have created. So that's pretty much in words what we just talked about in the slides earlier. Okay, good. I just need to change the slides and then we're back in business. Sorry? Yes. Okay. This one is a very interesting, most of these what I've presented are TED Talks, and they are 10 to 20 minutes long. Very inspiring talks, and some of them I couldn't link, but I think I could link this one. It talks about the combination between climate change, health, and poverty. Maybe you've heard there were elections in the US, and one of the big things that were part of the elections was migration or immigration or illegal immigration. It's a huge topic in the US. And the part that is troubling is when you compare where people are coming from to poverty, to the emissions, to the change in climate, it makes very compelling case. Then of course people are going to leave because they have no other way to go. All these things are interconnected and interrelated, and yet we want to ignore them, because if we take into consideration, then we would have to do something about it. It is linked. I think we'll try and run it. If it runs, it's great. If it doesn't, then it doesn't. So she makes a very compelling case, because the point is, no one leaves their home for nothing, right? There is always something that drives people away, and it is usually wanting a better life, either for themselves, usually for their children, usually for their families. And so the part that is really troubling is this whole thing of saying, no, wait a minute, we don't want anyone to come in and take away what we have built for ourselves. Because my atmosphere is your atmosphere. What I do affects you. And we know this because we have been measuring carbon dioxide levels at Mauna Kea or Mauna Loa. This is in the Pacific, the island of Hawaii. There is the big island, there are volcanoes there, high mountains about 3,000 meters high or higher even. And the University of San Diego put in sensors to measure carbon dioxide starting in 1960. And initially that was meant to measure the emanations from the volcanoes. It was just for volcanic activity. What transpired with that was there were all of these fluctuations, but it became a very nice climate tracker. I have a student from Kenya, and she was looking at these data, and she said, well, that explains it, and she has a very nice talk on it. It is on YouTube. I'll most probably will see it at some point, and I'll share the link with you. But the point that she's making is that it doesn't matter. This is in the middle of Pacific. There is no industry here. There's nothing. And yet, every year, the levels of carbon dioxide have increased since we started measuring. And so Chuck and I, we just did this, excuse me, we did this exercise. We said, well, can we overlay one graph on top of the other? So we adjusted the scales a little bit. This is the GAST, what we created. And by modifying the scales a little bit, we could overlay one on top of the other. Changes in levels of carbon dioxide in the middle of the Pacific, it's pretty much in the middle of the Pacific with no major industries around it, at an elevation of 3,500 meters. And so we are looking at a change that is happening on the levels of what we have not observed before. So I took that and I said, okay, what does it look like today? And this is what I could make out of the data. This is for land in brown, oceans in blue, and all of the data together in black. And these are now happening all the way up to 2024. The last data that I took from here was in which month? We are in November, right? So it was around beginning of November. So we had data all the way up to October of 2024, and that's what the data look like. So we do have a pretty dramatic change in this variation. And I took a base period of 1901 to 2000, which is silly because I should have rather taken something over here, 1900 to 1925 or something of that sort. But regardless, the point I'm trying to make is, regardless of where you take your baseline, the curve looks very similar, not much difference. Okay. So about out here, we don't have very reliable data for the oceans, right? So because the sensors were not there, we started measuring and getting much more reliable data here. So there is this whole system from UCSD where they have these buoys and they sink up and down and they measure the Argos. They measure temperature at different levels, and after some time they float around. After some time they come back up and they transmit the geographic and temperature data and other data, whatever they're measuring. And so we have much more reliable data now, and you see that they track. The reason they're not tracking each other exactly is because oceans take time. So it's a time delayed signal. So you don't measure that much here, but this will come at some point, will start showing you the change. And that's why we are always afraid of this curve being so being sensitive, right? When we see temperature change over here, we know we are in trouble because what is gone into this heat sink will take a long time to come out. And so that's the challenge that we're looking at. There's a time delay because it takes us a while for the oceans to catch up. And also it depends, I think what this is an average of ocean temperature. You have ranges, right? The shallow up to 700 meters is warmer, and then you have different stratification of the temperatures in the oceans. So that makes a slight difference as well.